Welcome everyone to your own channel, that is AP Physics. So now we'll be just hold on. So in the previous session, we have studied what is basically gravitational field intensity. Okay. So now we'll be starting with gravitational field due to a point mass. Okay. So now we'll be starting gravitational field due to point mass. Okay. Suppose you are having a mass. This is your mass M, capital M. Okay. So from the center at r distance, basically. From the center at r distance, suppose you're having some other mass, say m naught. Okay. So if we are being asked mathematically to find a gravitational field intensity of this capital M mass, so how you proceed? Very simple. We know E, which is basically a gravitational field intensity, is equals to gravitational force upon test mass. Okay. So this is our gravitational field intensity, which is force upon test mass. Now we know that gravitational field, that is the gravitational force, is what? This is capital G, capital M, M naught upon R square upon M naught. Okay, so now you can visualize this thing. This is deleted. So we can say G M upon R square. This is our gravitational field intensity. Okay. So we say Newton per kg is gravitational field intensity. And here we have, which is the unit as Newton per kg. Please note it down. I think we have already discussed this thing in the previous session. See, not only the principle of superposition holds for universal gravitational law or the universal gravitation force, it also holds for principle of superposition. Okay. So now, hold on, we have. Just wait for a second. So now we'll see principle of superposition for gravitational field intensity. So principle of superposition. Okay. So suppose you're having mass m naught. Okay. And in the vicinity of this m naught mass, you're having all other masses like m1, m2, m3, m4, and then. Okay. And suppose there is a attraction force between this m naught and all other masses, which is in the vicinity of this m naught mass. So let us assume the distance between these are, suppose it's R1, this is R2, this is R3, this is R4, and this is Rn. Okay. So if we need to find the net gravitational field strength of this m naught mass, how will we be approaching for this? Simple. We'll find gravitational field strength due to all these for this m naught via this m1, mn, m4, m3, m2. Okay. So it's simple. I'm just simply assuming you know all those things. So you will say net gravitational field strength will be equals to E1, E2, because all are vector quantities, isn't it? Since universal gravitational force is a vector quantity, so we'll say gravitational field intensity or strength will also be what? A vector quantity. Okay. So this goes up to what? En. This is the net gravitational field strength. Okay, please note it down. Now I'll be solving a question based on superposition principle of gravitational field intensity. Note it down so I can erase this. Okay, so now let us solve a question based on gravitational field intensity. Basically, the principle of superposition. So let us take a equilateral triangle. There are three masses at the vertices of equilateral triangle. Okay. So this is mass M, this is mass M, this is mass M. Okay. Since it's an equilateral triangle, we'll say the sides, the edges are all equal. So this is capital M, this is capital N, this is also one, this is capital N. Now, as per the properties of equilateral triangle, we know this thing that basically equilateral triangles, all the angles of the vertices are what? 60 degree. Okay. So the angles are 60 degree. Angles at what? This is 60 degree. So now you have been asked to find gravitational field strength at the center O. You can take this center as centroid of this equilateral triangle. Okay. So please find it out. How will you solve this? Take your time and try to solve this. See, again, it's a very easy class illustration. If you see, this is a line joining. Suppose this vertex is A, this vertex is B, this is C. So the line joining B and O is this. I'll name it as R. Same is the line joining A and O. This is also what? This is R. Same is the line joining O and C. This is what? This is also R. So all the distances are what? Equals to R here. So we see here, this is O point, this is a point O, and the gravitational field strength at point O, we know we have just derived for a generalized case. That is, if suppose we are having a mass, say capital M. So at R distance from this mass, if we want to write the expression for gravitational field intensity, we can write it down as what? This is equals to G M upon R square. This is our basic formula, isn't it? So same we'll be writing for this. I'll say here, vectorially, if you see the attractive gravitational field strength will be something here that is equals to Gm upon, because the mass is small m, so I'll be writing Gm upon R square. For C vertices, it's here that is Gm upon R square, isn't it? And for this also, it will be something as Gm upon R square. Gm upon R square. Actually, what happens in this, if you will solve this numerical by using all the geometrical values, you'll find that the vector sum of these field strength comes anti-parallel to Gm R square and also same in magnitude. So this basically cancels. And also by the property of symmetric structures, we already know this thing that the net force in the symmetric structures, where whether it's a square, equilateral triangle, hollow sphere, net gravitational field strength as per the superposition principle was what? Zero. So same holds for gravitational field strength principle of superposition too. Okay. So we'll say here the answer will be what? Answer will be zero. This is the net gravitational field strength. Answer will be what? Answer will be zero for this case. Okay. Please note it down. Okay, since now we have just till now we have just studied to find gravitational force or to find gravitational field strength due to discrete masses, simple masses m1, m2, and all those things. Now we'll be proceeding towards finding the gravitational field due to continuous mass distribution. Okay. Now we'll see gravitational field due to continuous mass distribution. Okay, so let's start. Suppose this is your x-axis and this is your y-axis. And this is a 2D plane, isn't it? So suppose, let us take a 3D one. So this is your z-axis. So suppose in a space, we are having some 3D structure, something like this. Okay. And on this, you can assume this to be like a rigid body, a massive rigid body. Okay. This is basically a massive, this is basically a massive rigid body. So now I'm going to take a dm mass on this one. So this is like a patch here, okay? So I'm going to take a dm mass on this. Now if the question arises that this complete body is having the mass, say capital M, and it's a irregular body. I mean, the mass distribution, the mass density changes. Maybe it can be for linear mass density, or areal mass density, that is surfacial mass density, or volumetric mass density. Okay. So now you have been asked that you need to find the gravitational field strength at any distance or at any point P, which is at a distance R from this body. How you'll approach? Your first generalized strategy will be this, that you'll be taking a dm mass on this. So first you will find a small gravitational field strength due to this dm mass. Okay. So as per this, my expression for small gravitational field strength will be, it's very simple. G, since this is the dm mass, so G dm upon the distance of the point from the mass, it is equals to R square. So finally, the next step, what is going to happen. As per the basic, we have studied in the basic mathematics, we studied what? Integration, to integrate the things. Okay. So here also we'll be applying what? Integration. It's very simple. And then you will solve the things. Okay. Let me tell you, in basic integration, in the basic maths section, I didn't told you about integrations, but more physical significance definition. So basic integration basically means to integrate all the particles to sum up and make it a big body. Okay. So now we'll say E net or net electric field strength will be equals to G R square dm. This is our net electric field strength. From this, you'll get a magnitude. Okay. From this, you'll get a magnitude. Please note it down. Okay. So since now you have derived the generalized case, now I'll be applying this case for uniform rod having the mass distribution capital M. Okay. Okay, so now let's check it out. So at first we'll see gravitational field strength due to uniform role. So we are having a uniform rod, mass capital M. So let's find the gravitational field strength. So this is our y-axis and this is x-axis. Okay. And suppose we're having from the edge of this rod, suppose this rod is having a mass m and length l. Okay. And we are asked to find at a distance a from the edge of the rod, there is a point P. Here you've been asked to find the gravitational field strength magnitude. How will approach? Our first step, we know it. We'll say, I'll go at distance x and we'll take a dx element. I mean, when I say I'm going to take a dx element, I mean that I'm going at a distance x. And when I'll take a dx element, it means infinitesimally small length dx element. Okay. So we know this thing that L length rod is having m mass. So unit will be having m by L. So dx will be having m by L dx. This is our dm mass. Okay. This is our dm mass. Got it? This is origin. And this edge is having the coordinates as L0. Okay. So now if we see how to find the gravitational field strength, we know this thing dE, which is basically a small gravitational field strength. Its formula is G upon R square dm. We can insert the dm from this equation. So we'll say G upon R square upon m by L dx. See, the thing is this. Here, if you see your R, this is actually, it's something variable. So you need to think and apply the formula properly. Their R was random. It can take X coordinate, it can take Y coordinate, it can take Z coordinate. So what you will be doing here is this. We will apply here X square. Okay. So I'll say, or what are you going to apply? Check. So when I'm going to apply the coordinates, it's very easy. So I'm going at X distance. My remaining distance will be how much? So this point is at A. If this is X, the remaining will be what? This is equals to L minus X. Okay. So I'll tell my R goes here, goes towards, we'll say, this complete distance of the point from the dx or dm mass is L minus X plus A. So I'll write here L minus X plus A and I'll insert here. So when you're going to insert here, you have to do definite integration within the limits. So this mass dx length mass, infinitely small length mass having the dm mass must be shifted from such a manner that it covers the complete row, that is from 0 to L. Okay. So here we'll say x goes from 0 to L. So now we'll see the integration part. So after solving it, doing integration, we'll get answer as electric field intensity. What was the limits? X must go from 0, that is the first part of the rod, to the complete rod, that is towards L. Okay. So after solving this, anybody please comment me the answer in the chat box. So your answer will be G M, okay, and it's A and B. This is your final answer, okay? Note it down. So you will say if you're having a capital rod of mass M and its length is capital L. So from edge of the rod at a distance A, there is a point P. If you need to find the gravitational field intensity or strength, the answer will be G capital M A L plus C. Okay. I hope it's clear to you. Now the next question arises. If we are able to figure this out, that if you're having a capital mass at a distance r, if you need to find gravitational field strength, the formula is very easy. It's very interesting too. That is gm upon r square. But suppose if we are having the gravitational field strength and the mass given to us, so what will be the gravitational force on that? This is a question for you. We'll say, we'll now learn force on mass and not in gravitational field E. Let's check. Okay. Suppose you're having a gravitational field intensity, something as E naught like this, and you're having a mass M like this. So if you need to find the force on this, we say force, okay, force upon mass is equals to E naught, okay. So the net force will be M E. Very easy. I mean, you just have to reverse the formula, then you get the answer. It was not that easy. Remember, by the rod, it is G. What was the formula? So if you're having, suppose this is a rod, and this rod is having the mass is capital M, and the length is capital L. So you will say at a distance A. Suppose this is at a distance A from this edge of the rod. So you'll say M mass, L length, and distance A. At this point, gravitational field strength or gravitational field intensity due to this rod of capital M mass will be G capital M upon A L plus A. Very simple. Okay. So G M denominator A L plus A multiplication. Very easy. Okay. So now let's move towards the next. So now we have some special formulas which you always have to remember. Okay. So we have seen that due to a rod, okay, I'll write all those formulas here. There is a complete list of formulas, but we'll only take the most important ones. So we'll say here. Okay. So at a distance A, if we see gravitational field strength, this is equals to G M A L plus A. Okay. At second, if you see, suppose you're having a arc. Okay. An arc is having the mass capital M. This is an arc. Okay. If it's an arc is of what? Arc is of it's particular a part of a circle. We know this thing. It's particularly a part of a circle. So suppose that circle is having the radius capital R, and this arc is subtending at the center of a circle it is basically a part of. It's subtending an angle phi there. Okay. So we'll say at that center, gravitational field strength will be given by this formula, that is Gm, very easy it is, upon r square, that angle, it can be 33, 35, 45, whatever, multiply by sine of phi by 2. See, this is a formula. There is a complete derivation for this, but we'll not go into the derivation. It's beyond the scope. You just remember the formula. So if I say it's something as 45 degree, so you write here 2gm, which is part of, which is the mass of basically this part, divided by r square phi. Phi is 45, means pi by 4. Sine 45 by 2. It means pi by 4 by 2 is pi by 8. It's not about for you to worry. I mean, sometimes we worry, we get a complex angles. Don't worry. In your exam sheet, you will having, if the question is given like this, they'll also give you the sine of pi by 8. No worries in that. Okay. Else, if the value is easy, you can solve it very easily. Okay. Please note it down. Okay. So you are able to understand that due to rod, the answer is G capital M A L plus A. And due to this, it is 2G capital M R square phi sine phi by 2. Okay. So now what we're going to do is, so now we must remember one more formula. That is, suppose they're having a ring, and a ring's radius is basically capital R. And at a distance, and the center is supposed it's 0, 0. And at a distance R from center on the axis. So we are basically talking about the axis. On the axis, this ring is having the mass m, the radius r. So if you have been asked to find on the axis, there's a particular point, say P. Here, the gravitational field strength or intensity is formula. So what do you write it down? It's very easy. You will say E net at point P is equals to G M R. Okay. So there must be no mistake in the formula. R square upon R square 3 by 2. Remember this? Okay, it's very easy. So due to a ring, basically, this is a ring, not a disk. This is a ring, not a disk. So suppose we are having a ring of mass capital M and radius R at a distance small r from the center at a point P. If you need to find the net electric field, net gravitational field strength or intensity, the answer is Gm small r upon r square, capital R square, 3 by 2. Okay. Now the question arises, if you're having the electric field, if you're having this formula for the gravitational field strength and intensity at a distance small r, G r upon r square plus r square 3 by 2, The examiner can ask you the question that at what r on the axis the point must be situated such that gravitational field strength or intensity must rise to pinnacle, that is max. So for this, what are you going to do? We'll use the concept of maxima and minima, in which we have seen in the series of the basic maths or basic mathematics. Okay. So what you're going to do is this, you will, for maxima, you directly do it. No worries. Don't do double differentiation and then let's do it. So you'll say dE by dr, you must put it to what? Put it to 0. Then you'll get the answer. So try it out. When you will differentiate it, you'll get the answer something as r plus minus r by root 2. This is your answer. So it means that basically at r equals to r by root 2 in the positive x-axis, and at r equals to minus r by root 2 on the other side of the ring towards the negative x-axis, the field value will be max. Field value will be max. Which field basically it is? It is gravitational field strength. Okay. Yeah, 100%, since it's an attraction, here also the force direction will be here. Here also the field or the force direction will be here towards the ring because it's attracting the mass. Okay. Now for this, there is a wonderful graph or curve which will be generating now. Okay, as per the expression, please note it down. Now we'll see a graph of this. Okay. So for a ring, we know it's Gm upon r square plus r square 3 by 2. This is a gravitational field strength. You all know this. Okay. So now as if we generate the graph, it's very easy. So for a ring, gravitational field strength versus distance r from the axis gives you the curve something like this. Okay. So the max point, you know that on the axis, the x coordinate must be equals to positive r by 2. Okay. This is a curve and this value is the max. Okay, let's put the value and find the answer. So at r equals to r by root 2, we get E max value for a ring is equals to Gm r by root 2 upon r square by 2, r square 3 by 2. So when you solve this, you'll get Gm r by root 2. This is equals to what? This is 3r square. So this is 3r square 3 by 2. This is upon 2. So this will go on the top. This will give you the value as 2, 3 by 2. This is E max. Is not enough. Okay. Very easy. Please note it down. Okay, I'm erasing this now. So after this, we'll also see gravitational field due to uniform spherical shell, hollow sphere, and then we'll draw the graph. Then we'll see for the solid sphere, inside, outside point. Then we'll draw the graph. And then we'll go towards the acceleration due to gravity near Earth's surface. This whole thing will cover in the next session. Till then, thank you. and keep watching this channel and please subscribe the channel. Okay, thank you so much.